All right, we're back at it. Today I did a Google search for homework, physics homework for solutions, and this was like the second hit or something like that. So here we go.
Let's look at homework number 4. All right, I will video this as well as put the answer key or take pictures of this and post this on Blackboard.
So right away, right? So the both modalities really to do the video and then have the actual product of the video be posted on the learning management system. Super smart, right? I mean, I think that there's probably some students who just look at the result and say, "Yep, got it," and there's others who are like, "Huh, what?" And they can just go right to the video. So I think that I sort of like that idea. I tend not to do it when I make videos. It's sort of on Scratch on a digital screen, and the product I usually don't bother to post. So I'm intrigued by this idea that both do the video and make the thing available. And I wonder if there's anybody who's actually tracked sort of download statistics of their students of one versus the other.
As well for you. I hope it's helpful. 2020. So please go back and at least maybe double check your answers versus the answer key. Hopefully it'll help you out some. It says here that a ball will roll off the edge of a cliff. Again,
So really, really interesting, right? So just in the middle of reading the problem, already starts to do the drawing. So it's so that there's sort of something to refer to as she reads the rest of the question. Obviously, I'm sure she knows what's coming up, but it's sort of interesting that the idea of immediately converting the text into a representation that might be more useful or a different way to think about it. So already drawing the cliff, that's not how I would have drawn a cliff, right? So there's already something interesting. If I can read the rest, to reach the ground below, how tall is the cliff? Aha! So it says it takes 10 seconds to reach the ground below. I'm not sure if she's actually drawing the cliff or the trajectory of the ball here, so let's see.
of us, I see us having problems on the quiz. I see you having problems on the homework, but again, I'm not seeing any drawings happening.
That's awesome.
Here's a ball. It's rolling off of a cliff. Okay.
Now, there is a famous problem in physics. It's typically for in undergraduates, it'd be like junior year. That's all about like where does the ball lose contact with the cliff? And that is a really, really interesting problem. And fascinatingly, I'm trying to think, well, the rolling, I guess, screws it up a little bit, but the result, I'm trying to think. I guess the result would change the time it takes for that problem to land at the bottom. Usually it's a ball rolling off of a hemisphere. And so as it goes, it gains so much speed at some point it loses contact. And that one would take longer than this. I assume here it's rolling off the cliff. So it's literally not going to be touching. And so it really is just going to be free fall.
As it rolls, it has a velocity because it's moving this way. It's going to fall off.
People always make fun of me for my sound effects. See, it's useful. Now go back and listen to that again. You got to admit that was super awesome. As she put in the dash line of the ball. Also love the colors, of course, and recognizing what we know. It says the ball is rolling, so it must have a horizontal velocity. That's super cool. So already she's putting a lot of interpretation into the problem as she is, just really at this moment setting it up.
Like this. It takes 10 seconds for it to reach the ground below. So while it's in the air, t equals 10 seconds.
Cool.
The next step that you're going to do is you're going to x and y component because I see a parabola was formed.
Yes.
X and y.
Ooh.
DTV, DTVIA, and then yes, VF, but
Wow. Okay. So there's a whole lot here. First of all, the chart to really separate the X and Y, very, very cool. Recognizing what's known and what's not known. Now she could have put some A's and V finals over on the X column. So she's already saying, oh, good Lord, there's no acceleration in the horizontal direction. I'm not going to bother. But like I've talked about in some other videos, giving students tools that work, right? Like simple problems, hard problems. Look, here's a great way to start. Here's a way to think about it. What do you know in the X? What do you know in the Y? And so right away it's like, okay, X is boring. Y must be where the interesting stuff is. And obviously there could be a follow-up question like how far away from the cliff is the ball when it lands, but that's not being asked. And so I'm curious to see if she actually evaluates that. That would be, I guess, the D for the X one.
It's not even used.
Oh,
A is 9.81. VI is 0. T was 10 seconds. D was not given to me. D was not given. T is 10 seconds. And V was not given to me.
did you hear that hitch? Did you hear that pause? She realized that she knows that the X column is basically not needed to answer this question. And so I heard a pause, I heard a hitch when she was writing down the V of the X. She's like, oh boy, I don't know that either. She knows she doesn't need it. But she was pausing because I think, you know, she wants to show the scaffolding, super cool, and she wants to indicate that it can be useful. I'm wondering if she's going to come back and say, well, yeah, we didn't give this, but we didn't need it. Or it really, I think it's totally fine to have the students focus just on the Y column, like, oh, wait a minute, this is all we need. Let's go crazy.
So now I have my X and my Y components filled in. How tall is the cliff? Okay, well, I guess I started writing things in before I read the whole thing. The question is from here
Awesome.
to here,
That was a super cool
how
eraser.
tall is that? I'm going to put a question mark there.
Wow, and you can write. Oh, it must be liquid
Here,
paper.
my
Very
highlighter.
cool.
What side am I looking for? I am looking for the Y component side.
So here's my question for you guys. Multiple colors, highlighters, all of that stuff it produces a solution that doesn't look anything like what the students are doing. The students are very, very likely going to do it in monocolor. They might draw some boxes around some things. There's no question that this is useful as a teaching aid, but how do you motivate the students? Well, maybe you do motivate the students to use highlighters and things like that. So I'm curious about the difference in not quality really, but almost like technology or multiple tools that you put in your solutions that you post versus what they know their own pages look like.
In your notes, it tells you that when it comes to the Y component side, there is an equation that we're going to use. D equals 1/2 AT squared. This is going to work 90% of the time. Again, there are a few times where it may not work, but 90% of the time, this is going to be the one that works.
So really, really cool, right? Like, hey, you guys have this thing that we've been using like crazy, and 90% of the time it's going to work. I wonder if it's worth it to qualify that, right? Like 90% of the time of these gravity problems, or 90% of the time of the homework we're going to be doing, or are we saying this is going to work 90% of the time in your life, right? I know that there's some physics teachers that I interact with who are kind of frustrated at the amount of energy we put into constant force problems, constant acceleration problems, and they think, good Lord, you get to springs and the students really struggle with that, and honestly, gravity, if you go really far out, that's not constant either. But I also think that this notion of developing some intuition of how things fall sort of in real life, not super high altitudes and things like that, and also this sort of comfort, like, hey, we've got this tool. Let's really, really tease this tool out and make some really interesting predictions that are going to match your everyday experiences. So I think that to occasionally warn them, like, oh, remember, it's not always going to work, I think is smart. But how valuable is it to stop and say, well, here's a list of 5,000 applications where it's not going to work. That's probably not smart. It reminds me of all of the work that I do when you get into modern physics and say, you thought that momentum was m times v, haha, gotcha. You thought that F equals ma, haha, gotcha. You thought that kinetic energy was 1/2 mv squared, haha, gotcha. Right? It's just, the students just feel torn down. They just feel torn down. They're like, ugh, what? Well, then I'm not going to trust you now. So I'm just really intrigued by how you guys sort of handle these let's call them approximations, what the hell, as people are learning and starting to learn how to flex their muscles, their physics muscles.
Let's try it. D.
Let's try it. I love
Now
that.
I'm going to convert to 0.5, 9.81. Yes, I do know it's a negative because it's going down. And T is, they told me 10 seconds. and I need to square it. Okay? Let's go ahead and do that. Let me square this 10 first and make that 100.
So 49, I think. 49 meters?
So
That's high.
10
Was that 5 stories?
squared
10 meters per story?
times
So
9.81
taller than any building on my
5
campus?
equals 490.5 meters. Yes, it's a negative value
Oh.
because it's falling down.
Oh, right. I was off by a
That
factor
is
of
the
10.
correct answer.
Holy cow.
This was a one.
Did you see that? So I made this mistake. I'm like doing this math really fast. 98 divided by 2, 49. And I convinced myself that 10 seconds for a 5-story building was right. And I'm clearly wrong. I mean, I'm off by so much. So 10 seconds of free fall. 10 seconds is a long time. Just hold your breath for 10 seconds. 10 seconds is a long time. And so a 5-story building is going to be way less than that. So how do you deal with, I just made a mistake. How do you deal with your students when you do a mistake and you maybe go off on a tangent too far before you grab your calculator? First of all, hey, look at these significant figures. Who cares? Super awesome. I also wanted to comment on, she said, hey, let's just go ahead and try it. I think that now let's see if she goes back to the X column or not.
Step problem. The majority of the parabola problems are 2-step, but this one was a 1-step problem.
Cool. Very cool.
Number 2.
All right, we'll stop there. So very, very, lots of interesting stuff going on here. I think that there was an X part she could have done if she said, well, let's see, I wonder how fast it was rolling, or imagine it was rolling. She could have just dumped in some velocity there. But I think that what she said at the end was super cool. She's like, look, a lot of these problems have an X and a Y, but it turns out this one was almost like a warm-up. It's like, it's fascinating. If all you care about is the height, then maybe you can just ignore the X. And in fact, right, it doesn't matter how fast it was going horizontally. The answer would be the same. And that, of course, I think students really find that interesting. Actually, let me see if I can find it. I thought I saw the very beginning. Let me just, yeah, there it is. So right here, it's building up to a problem that students love, right? That it turns out that they're all going to land at the same time if they leave the shelf horizontally. So that's really cool. Well, thanks everybody. Happy Monday. And remember, physics teachers are awesome.